Okay, so today is Friday, November 20th, 2020, a day that will live in history. And today we're going to do hidden Markov models in ECE641 model-based imaging. So we basically have this lecture and the next lecture in person, and then we have the Thanksgiving break, and after that it's kind of like going to be a little different. So we'll be doing remote lectures. Maybe we'll just do Zoom. I'm sure we'll do Zoom. Maybe we'll make them a little different. But okay, so, oops. Hidden, okay, well, I'm not even sure. Okay, hidden Markov models. Because I want to go through this material quickly, I'm going to emphasize pictures, okay? So this is a hidden Markov model. You have a Markov chain, so the x's are discrete. Then this is a state transition in time. So like I told you, there's two different ways of sort of talking about, drawing, not talking about, but sort of drawing Markov chains. You can draw them as like time sequences, right? So each circle represents a different value of the state in time. Or you can draw them as state transitions, like, so each circle represents a different state. Okay, or you can actually do both, because you could have like all the states and then in time, but you know. But so this is useful, this kind of drawing is useful when you want to look at what the dependencies are between states as a function of time or space. So each of these circles can take on one of m different discrete states. We have an initial one because that's your initial condition. Usually that's set. And then you have this thing, and you go like that, right? Now, for each state, there's a corresponding observation. And the observation depends on the state. And the arrows represent sort of conditional independence. So y is conditionally independent of everything else given x, right? Now there could be different dependencies here, and the y's could be either discrete or continuous, although typically like in this, for most of what we'll talk about here, maybe all of what we'll talk about, y will be continuous, because it works for the discrete case too. X really has to be discrete because we have to do, for what we're doing here, because we have to do sums and things, okay? But, so what'll happen is this, if you look at if you take out these connecting things here, this could look like a Gaussian mixture distribution. Because each state is a class, like that's sometimes they call a latent class. Okay, latent means you can't observe it directly. So this is a class, and then this is an observation, and the mean and say variance, if this is multivariate Gaussian, of the observation, it depends on the particular class, right? But the states, but then this is sort of, so you can think of this as a generalization beyond Gaussian mixtures. Because now what you're doing is you're linking the states together in time. Remember before you kind of said, well, you know, we have these states, but you know, how are they related? And the answer is, well, they're not related, they're independent. So you say, well, why do you order them from, you know, 0 to n? Well, because you got to do something with them. So it's just a matter of like counting them, okay? But you could really count them in any order, it didn't matter. Here the order matters now, because they're ordered in time, okay? Now, this model used to be used for things like speech recognition. It used to be pretty popular. It's not, I think it's pretty, hidden Markov models have been largely, I'll say, because I don't really know, displaced by deep neural network models, which do similar things. Because deep neural, if you have a recurrent, neural network, it's essentially like a generalization of this, really. because you have, in a recurrent neural network, each new state, there's inevitably a state in a recurrent neural network. And each new state is depending upon the previous ones. So it's essentially a generalization. Although the state may be continuous instead of discrete. And then there's some kind of observation. But the beauty of hidden Markov models is that you can get closed form calculations for a lot of things that are kind of interesting. Okay, and it's what they call a doubly stochastic random process, because the y's are dependent on the x's basically. And you could actually imagine extending this to even more layers. Okay, so that's the idea. So this is what's called a generative model, because you can generate samples from the distribution. So it's easy enough to do that because you start with some, like let's say you could either have the initial state be deterministic or random. If it's random, then you pick some distribution. Remember, it's discrete and finite. So there are m states. So in order to specify this distribution, all you have to do is specify the probability of each of those individual states, right? So how many numbers does it take to specify the distribution of this first state? 3. Well, in general, if you have m states, how many numbers does it take? It sort of takes m minus 1, but it takes m, but there are really only m minus 1 degrees of freedom. Why are there only m minus 1 degrees of freedom? What do you know about those m numbers? So I have x0, right? That's a random variable. It's the value of this first initial state, right? And it's equal to m. What does that m represent? It's the state, right? It's the value of the state. x0 is a random variable, but that's just a number, right? And then that's the probability that the state's m, right? And then this thing is equal to y. I have some notation I use for that.
IM?
Yeah, it was like tau m. It's something m, whatever you want to use, right? Now, what do you know about those taus? Tell me the conditions. Can I pick any taus I want? Can I pick absolutely any taus? No. What do I need to do when I pick those taus? They have to sum to 1, and what else? They have to be strictly non-negative. They have to be non-negative. They don't have to be strictly non-negative because they can be 0. But they can't all be 0 because they have to sum to 1, right? Okay. And it's okay, fine. So you specify that, and then you generate a random variable. Do you know how to generate a random variable with that probability distribution? How would you actually do it? If you had to do it in MATLAB, say. Does anybody know?
You could do uniform 0 to 1 and threshold.
Yeah, you take a uniform random variable between 0 and 1, and you threshold. What would the thresholds be? So there would be like a uniform random variable between, this is 0 and 1, and where would you set the thresholds?
Each of the towers.
So the first one would be what? Excuse me? Say it louder.
Tau 0 times.
It would be tau 0. See, if you say a lot of answers, I'll just pick the correct one. And then the second threshold is where?
Tau 0 plus tau 1.
It'll be tau 0 plus tau 1. And then so forth and so on until I get to the top one. And what will that be? Yeah, it'll actually be 1 minus tau m minus 1, actually. But that's also equal to the sum from I equals 0 to m minus 2 of tau I, right? So that function, by the way, I just want to point out something, which is that function looks like what? So it's constant and like this, and it jumps like that. Each one is, this is 1, 2, 3, like this. And then they'll be like, and this will be m minus 1, I guess. Right. Right? It'll look like that, a stair step. Correct? This function, by the way, is exactly the thing from problem 2. Remember problem 2, the infamous problem 2, where you had to calculate, this is the inverse cumulative distribution function of the probability distribution for x. Okay? But intuitively, that's what you're doing when you generate a random variable. You always start with the uniform distribution, and then you do something to it, right? Because you have to put the uniform distribution random variable into the function, which is the inverse cumulative distribution function, right? See, it all makes sense. It just seems weird, okay? Okay, now, the x is, okay, so now that's how you generate the first random variable. You can generate that random variable, right? Can you generate x1? How do you generate x1?
State transition probabilities.
Yeah, so you take this x and use the state transition probabilities. Be a little more specific. What do you actually do? You're writing the code. You know, that's why I think writing code is good, because there's no, I mean, you can write all kinds of weird symbols on the board and say, oh, yeah, yeah, and try to pretend you learn to shake your head really sort of knowingly and so forth. But when you write code, that's where the rubber hits the road, okay? Because you got to actually write some code that does something, and if it doesn't do the right thing, the wrong thing comes out, okay? So if you're going to write code to generate x1 from x0, what would you do? Excuse me?
Multiply by pi.
Well, you can't really. I mean, what the heck does that mean? Not in the code. Because when I multiply by pij, that doesn't really calculate the random variable. What does it calculate?
Do the same thing all over again, but with transition probabilities.
Yes, okay, but that's correct, but I want to, because Sandra, your point was a good one. It's the natural answer, okay? But it's not the answer to the question, because when you take, say, tau 0 and you multiply by p, what does that produce? Yeah, what we call pi 1, okay? Right? And is pi 1 the random variable? Is this random?
No, that's the distribution.
That's the distribution of the random variable, right? There's a difference between the random variable and its distribution. So when we say we're going to generate, we have a generative random process, we have a generative model, it doesn't mean that we can calculate the probabilities. Well, it may mean that, but that's not what it directly means. What it means is we can generate random variables with the correct distribution. So the way we generated the random variable x0, we had its marginal distribution. We can use that to compute, to generate a random variable, right? And this is all predicated on the idea that you can generate uniform random variables. But there are like well-known ways to generate pseudo-random, uniformly distributed random variables, okay? That's the kind well understood. But, okay, so but we know how to generate a pseudo-random variable that has this distribution, right? Then how do we generate the pseudo-random variable x1 from this?
You do it the same way with the new distribution that you obtained through the transition matrix.
Right, right. Now what does that really mean? Now you have this P, right? This is Pij, okay? And what happens is that when you generate the pseudo-random variable, you actually get a number, okay? Now what do you use that number to do? You know, it's the simple things in life that are hard. The hard things are easy. So you've generated x0, you got this matrix. What do you actually do? What do you actually do to generate x1? So you got x0 here, and then you want to generate x1. So you generated the random variable. It's not really the random variable, because the random variable is a function, okay? By the way, someone pointed out that random variables are neither random nor variables, okay? Maybe it's a poor choice of names, but that's what they called them, okay? Random variables are really functions. They're functions from omega to r, okay? But that's okay. We think of them as these random events, like with random outcomes like coin flips, okay? So to simulate that, we can use a pseudo-random number generator in a computer. The pseudo-random number generator in the computer doesn't really generate a random variable. It just generates a number, okay? But it does it in a way that its distribution is according to the assumed distribution, right? So there's really three things in that sense. There's the probability distribution, there's the random variable itself, and then there's the pseudo-random variable that's sort of what we call a realization, whatever that means, of a random variable, okay? So now the program generated our pseudo-random x0. What do we do next?
Super low.
Excuse me?
Pick a row from the transition matrix.
Yes, could you say that a little louder?
Pick a row from the transition.
Yeah, we pull a row. Which row do we get? You get the x0th row. So essentially, the way to think of it is you have a random index. Okay? The index into the matrix is random. Now what do? You generate x1, and how do you do that? You do this technique again, okay? Only now you don't use the towels. What do you use? You use the entries of this matrix along the row. Does that make sense? Is that clear? Now, once you've done that, so is that clear? Does anyone have any questions about that? It's a really important point because it's very conceptual. Okay? So now to do x2, what do?
You do the same thing using x1, the x1th row of the Pij matrix.
Yeah, you just wash, rinse, repeat, right? Wash, rinse, repeat. You just keep repeating it, right? Once you know how to do it the first time, you just keep repeating the same process, right? So we know how to do that. That's just a for loop, correct?
Yep.
How do we generate the y's? So these are our pseudo measurements, right? How do we generate them? This is for simulation. In real life, the y's may represent some physical measurement in the real world. Then we just collect the data, okay? But the question is, if we have this generative model and we want to simulate the generative model, how do we generate the y's from this?
Sufficient statistics.
Excuse me?
The sufficient statistics of the x1.
Well, okay, so you take x1.
And then the distribution given x1.
So I haven't actually told you what the distribution of y is yet, right? So I'm sort of, there's no answer to my question in a sense. But let's say that we say yn is distributed, the yn given xn, right, is going to be given that xn equals m, right, is going to be distributed as normal with mean m and covariance m. Okay? Right? So do I know how to generate a Gaussian random vector with mean m and covariance rm? By the way, how do I do that? Okay, so one answer is you call the MATLAB or Python routine, right? And that's a perfectly valid answer, okay? Okay, it's a perfectly valid answer. I gotta give you credit. That's the engineering solution, and you should be proud of that. But if you didn't have access to the MATLAB subroutines and stuff, what would you do? How do you generate a random variable with this distribution?
Generate a zero mean variance 1 Gaussian random vector, and then you would add the mean, and then you would multiply by the covariance matrix.
Not quite, but you're on the right track. I'm very proud of you, okay? We actually did it, I think, didn't we? Okay, I think we did it. How do you do that? This is good background, okay?
It's like for 1, it's square root sigma times the zero mean variance 1 plus the mean.
Yeah, so what happens is, let's say we have R. First of all, you have to decompose R in terms of its eigendecomposition. Okay, right? Then what you do is you take, and let's say W here is distributed as N0I, okay? So that's easy enough. You generate, if this is a p-dimensional vector, you generate p-independent Gaussian random variables, stack them up, and that's got mean 0 and covariance I. The fact that I is diagonal, what does it tell you? That the what? They're independent or uncorrelated, really. Okay, they're uncorrelated, but they're independent because it's Gaussian. Okay, good. And what does it tell you about their variance? 1. Okay. So if we take y equals, we take w, we multiply by lambda to the 1/2. Why do we take the 1/2? Well, we'll talk about that in a minute. And then I'm pretty sure, hold on, I gotta be careful here. Yeah, and then we multiply by e, okay? And that does it. Intuitively, lambdas are like the diagonal matrix of variances. But you need to multiply by the standard deviation, so you have to take the square root. You multiply by e, that rotates the distribution so that it's properly correlated. So then what happens is that, and you can actually do the thing, the y transpose is equal, you could do the calculation if you're not sure. In fact, I'm not really sure. I wouldn't implement this if my life depended on it, okay? I'd double check because I could make a mistake unless I wanted to really live dangerously. The transpose of lambda is itself because it's symmetric. It's diagonal, okay? So I can take the expectation, the e's, okay, this is like a squiggly e, okay? Those are, I'm sorry, I used the same letter. So this is E lambda to the 1/2, the expected value.
WW transpose.
Oh, this is WW transpose, yes. Thank you. Right? What's the expected value of WW transpose? I, because that's what the assumed covariance was. So this is I. So this is equal to E lambda E transpose. Because if I multiply lambda to 1/2 times lambda to 1/2, I get lambda. So voila, the answer is correct. Okay, so now if I take this plus mu, I get the correct mean, right? Okay, so my point is I can generate, oh, and by the way, you don't know how to generate Gaussian random variables, but it's not that hard actually, okay? There's a linear transfer, there's a transformation, it's not linear. There's a transformation of uniform distributed random variables that will produce Gaussians, okay? Actually, here's what it is. It turns out that the integral of the Gaussian distribution is not closed form. It's like a classically hard integral. It's called the error function. So what you do is you take two Gaussians, okay? Okay, you take two Gaussians like this, right? So one Gaussian this way and one Gaussian that way. Then it turns out that the distribution of the magnitude is, does anybody know what actually the distribution of the magnitude squared is what? Does anybody know?
Exponential?
It's exponential. Actually, could somebody pull the door closed there? Because I don't want to disturb the people, but because if you add, it's actually technically chi squared with 2 degrees of freedom, okay? And it turns out chi-squared with 2 degrees of freedom is exponential. So you can generate an exponential random variable. And then what's the distribution of the phase? If you have two independent random variables, right? What's the distribution of the phase angle here?
Uniform.
It's uniform on 0 to 2 pi, right? So you generate a uniform random variable on 0 to 2 pi, which means you just take a uniform random variable and multiply it by 2 pi. And then you use an exponential distribution. You take the square root. You generate a random variable with an exponential distribution. Take its square root, I guess. Then you transform from polar coordinates to rectangular coordinates, and you get a pair of Gaussian random variables. Okay. Okay, I don't know why, I just feel like you should know this, okay? It's nice to know that the stuff, all the magic can be like done, okay? So my point is this. So let's go back. So you know how from first principles to generate this distribution is my point. How generate samples from this model, right? You know how to generate this sequence of discrete random states, right? And then you know how to generate an observation for each state. How do you do that? For each state, you take the actual state, like it's the number, it's 3, or it's 17, or 2, right? Whatever that discrete number is, that discrete number is always between 0 and m minus 1, right? You take that and you have a table. The table has, if you have like say 17 states, then your table has 17 entries in it. Each entry has a value for mu and Rm. So you take that state, you index into the table, you read off the value of mu and Rm, which are actually vectors of matrices, okay? And you use them to generate your random variable y, which is going to be a Gaussian random variable or pseudo-Gaussian random variable with mean mu and covariance Rm, right? So now you can generate samples from this distribution, correct? Okay, now that's fine. So it's a generative model, right? Now we're going to say, okay, if I have the observed y's, I'd like to be able to do different things. One of the things I'd like to be able to do is call state estimation, okay? In state estimation, I have the observed y's and I estimate what the x's are. That's just like doing the classification when you were doing clustering, but you're making here a hard classification, and they're related spatially. The spatial relation is very important because it may be that the signal to noise for making a decision at any time is very low. But there's a lot of correlation in time. So the fact that there's correlation in time can be used to do a better job. So let me give you an example. Okay. Let me give you an example. Oh God. Example. So you have some intuition. So let's say that you have a Markov chain that has two states, 0 and 1, right? So it's like dum dum da 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 da. I'll make it longer, and then all of a sudden it jumps to 1. Okay, because let's say that it's like that thing we gave in the beginning where the probability of transition is small. Okay. And let's say in state 0, what happens is that for x equals 0, what we have, so we'll say mu 0 is equal to 0, and sigma 0 squared is equal to 10, okay? Or let's take a power of 2, 16, okay? And mu 1 is equal to 0, and mu 1 squared is equal to 1, okay? So the variance, the standard deviation of this is 4, and the standard deviation of that is 1, right? Right? So what'll end up happening is it, okay, I'm not going to, ideally I would draw it like discrete, but it's too hard, so I won't do that. I'll do it like this. It'll go like this. Of course, it's supposed to be like white Gaussian noise, okay? That's my rendition. So you're looking for the place at which the behavior changes.
Shouldn't it be the opposite? Like, wouldn't it be?
Oh, I got it reversed? Okay, there's a simple solution to that. Okay. All right? Sometimes, like you can use this to detect when the washing machine broke. Because over here it's broken, okay, and here it's working right. And then all of a sudden what might happen is that all of a sudden, you know how the washing machine is? Like, then all of a sudden, for some reason, it starts working again. Usually when the repair person comes, because it's like, it gets scared, and it thinks, okay, yeah. Okay. And then you would say to him, then you say to the repair person, it was making a funny sound, really, okay? Yeah, or the automatic, that always happens to me. I have a 99 M3, okay? And like it always makes weird sounds until I bring it into the dealer, okay? And then it behaves itself. Okay, all right? Now here's the thing. Now you can easily imagine that when you're looking at this, you need to find the time at which that transition occurs, right? And it may be hard to tell. What if the standard deviation is almost the same? Or right? Maybe they're really close. So this is 1, this is 15, okay? And that's 16. So in that case, it looks like this. It's just a little bit bigger. You see? So you look at it and you go, oh yeah, it looks like it started getting, it looks bigger here and it looks smaller there. And you're like, well, where exactly? Is it like here? Is it, when did it switch states? Okay? So the value of the hidden Markov model is that you have this model of correlation in time that you can use to try to estimate the state transitions. Also, what happens here? Like if over here it was like here, it's like just random fluctuations, or did it switch states for a few times? You're not sure, right? So the hidden Markov model, you'd like to do state estimation to determine what the states are. And it's sort of got popular, hidden Markov models, in speech processing for, these would represent, states would represent phonemes. Okay? So you'd like to do state estimation. In order to know to do state estimation, you need to know the model parameters. So what are the model parameters? The model parameters are what? It's going to be, first of all, you need to know, for each class, you need to know pi. Okay, we need to know, okay, why? We need to know tau I for I equals 1 to n minus 1. That's the probability of the first state, right? You need to know Pij for I and j equals 1 to n minus 1, right? That's the transition probabilities, right? You need to know, I'm going to do it, mu I for I equals 1 to n minus 1, right? Those are the means of the observations. And you need to know Pi for I equals 1 to n minus 1, okay? And then that's the full set of parameters for the model. So what is this parameter? Excuse me? This is the probability of the initial state. What's this? This is the state transition probabilities, right? What's this? It's the mean of the observation y, given that you're in state I. And what's, oh, this is the wrong thing. This is R. What's this? So this is a matrix, that's a vector, okay? So you need to know all those things, right? So if you want to map estimate, the map estimate is x hat equals the arg max over x of p of x given y and theta. That's okay. That's the map sequence estimation. Okay, so it tells you the your x here is the full set of x's at all time. So you're jointly finding the set of x states that maximizes the probability, the posterior probability of the x's given the y's. That's distinct from picking a single value of x. There's also a thing called MPM where you pick one x at a time and you just pick the single x to be most probable. So the distinction is this. When you're doing map, you're finding the most probable sequence, okay? If you estimate each state individually, you're just doing that one state. So if you did each state individually, you might get a sequence which would occur with probability 0, right? In other words, you're picking each state to be its most probable, but the sequence might not make any sense. Okay? Okay. Now, okay, so that's fine. That's called state estimation. But that's not the really hard problem. The really hard problem is parameter estimation. So the state estimation, this is state estimation. The state estimation problem is the practical problem. It's actually the useful problem. Okay, well, they're both practical, but that's the actual problem. That's like the pay dirt, okay? That's the outcome. You really want to do the state estimation because usually the state's the thing you actually want to know. But in order to be able to estimate the states, you need the parameters, right? So you need to estimate the parameters. The parameter estimation this is really training, typically. I mean, it doesn't have to be, but it typically is. So this is like when you have a deep neural network. I'm talking, it's really sad that I have to explain everything in terms of deep neural networks. It's really kind of, but what are you going to do, okay? In your deep neural networks, you train the deep neural network. This is like the parameters of the model, okay? And then this is more like the inference. This is when you apply the model to actually get an answer to your problem, okay? But you need to train the model in order to be able to use the model. So the really interesting thing is that how do you train a model like this? Now, if you have the x's and the y's, if you have the complete problem, you have the x's and y's, it's easy to estimate the parameters. Why? Let's just look at the x's. If I actually observe the x's, if I have them, right? First of all, if I have the x's, I mean, it's almost degenerate. If I only have one value of x, so I say, well, okay, so I have one observation. The initial state is 2, okay? So then what's the probability distribution? My maximum likelihood estimate for the probability distribution of the initial state. It's probability, the state 2 is equal to 1, right? Now, if I had multiple observations, then I'd like have them vote, right? But okay, so don't worry about that. Now, the transition probabilities, Pij. How do you calculate the maximum likelihood estimate of the transition problems? What's the obvious thing to do? It's a homogeneous Markov chain, right? You just have a set of states. How are you going to, if someone asks you, and you didn't know anything about this class, what's the probability of transitioning from state 2 to 5? What would you do? You'd sum you'd form a histogram of all the pairs of changes, right? Now, the histogram isn't the probability distribution itself. To make it into the estimate of the probability distribution, you have to normalize it so it sums to 1. Okay, so that's this. Hold on. Here it is. Parameter estimation. So what you do is this. So you form, these are the sufficient statistics, the n's and the k's. The n's is just for the first state. That's sort of trivial, okay? Because unless you have multiple observations, this would come into play more if you had multiple observations of the same Hidden Markov model. In other words, you saw the same sequence occur multiple times, so you could see more than one initial condition. If you only have one observation, then it's kind of silly, right? Okay, but okay, fine. But the k's always work, because here the k says I look at Kij is I sum all the times that I have a ji transition. Okay. I don't know why I did it that way. And, oh no, ij transition, because that's n minus 1, okay? So this is an ij transition, right? You look at how many times, and you sum over time. So you count the number of times you see. Let's say you have k 2, 3. You count how many times you get a 2, 3 transition, right? Now, if k 2, 3 is large, that doesn't necessarily tell you that the 2, 3 transition is probable, because it might be that 2 just occurs a lot. It's like the same fallacy we just had, fallacy of logic, okay? That you say, if you meet a Purdue student and they're very gregarious, is it more likely they're an engineer or a theater major? Of course, you're supposed to say it's more likely they're a theater major, because you'd say, well, engineers are not, don't have good people skills, which isn't true, okay? It's a bias, but I'm an engineer, so I'm picking on myself, okay? But that's a fallacy. The answer is it's an engineer. Why? Because there's way more engineers at Purdue. So that the prior probability is a lot larger. Okay, so that means that the posterior posterior probability of them being an engineer is still much higher, okay? In fact, I don't know, do they have theater majors here? I don't think they do? Okay, because they have okay. Anyway, yeah, I love theater majors, okay? I'm not picking on the theater majors, because I'm gonna get, like, pummeled or something. Okay, but anyway, so IJ, okay, right? So you have to normalize it. If you want the conditional probability, so the maximum likelihood, so you go through the calculation, and the maximum likelihood estimate is this. So the maximum likelihood estimate, so this is p hat because it's the maximum likelihood estimate. The maximum likelihood estimate p ij is just, you take the k's and normalize them so they sum the 1 in the index j. They have to sum in the over 1 to the index j. So for each I, you divide by the k sum over j. If I really wanted to be picky here, this j maybe should be another letter, but I use the j there because I think it causes less confusion. All right, does that make sense? This is the obvious thing. It turns out to be the maximum likelihood estimate, but you'd have to prove that, okay? The problem is you don't have the x's, correct? So how do you do it if you don't have the x's? If you don't have the x's, that's when the things get tricky. So you can apply the EM algorithm. We're going to use the EM algorithm. It turns out that the k's are the natural sufficient statistics for the exponential distribution of the Markov chain. So for the EM algorithm, you need to really calculate the posterior expectation of k given the observations y. But that requires that you compute the probability of x given y, and that's hard. Okay? That's hard because of the complex. This is what's called a graphical model, by the way. You may have heard that term. Okay? That's what a graphical model means. Anything where you draw a graph. And if there's no loops in the model, then there's no loops in the graph. Then this is not a loopy graph model. Which is, okay, anyway. So we need to find the posterior distribution of x given y. So how are we going to do that? Well, turns out there's a magical algorithm. I love this magical algorithm. And it's very closely related to dynamic programming. Okay, for state, there's not going to be enough time. We have to break this thing in. To do the magical algorithm, the magical algorithm is called the forward-backward algorithm. So we have the present, we have the future, we have the past. And there's two things we want to do. We want to solve this map estimation problem, but we also like to compute the posterior distribution of x given y. They're very closely related, but they're a little different. Because in one case, you're maximizing over x, and the other one, you just want to compute what the distribution is over x, okay? So for the maximizing, you use dynamic programming. And if you can read this, and maybe I'll skip it because there's not going to really be time. You solve a dynamic programming problem. This is the dynamic programming problem. You just do this recursion. The F's here are the probability distributions of the Y's given the corresponding states. L is the thing you're trying to solve for, so that's the thing you solve in the recursion. And the P's are the transition probabilities. But all this assumes you know the P's and you know the parameters. The thing, I'm going to kind of skip that, but I'm going to talk about the forward-backward algorithm. The forward-backward algorithm is pretty cool, okay? The forward-backward algorithm is very closely related to dynamic programming. It's a little different, okay? And you do this one pass forward, one pass backward, and it allows you to compute all the marginal probabilities of the states. And it works because of the linear structure of the hidden Markov model, because it's not loopy. If the thing was loopy, you can't do it. So that's the algorithm that I'm skipping for the forward-backward algorithm. Okay, the forward-backward algorithm is pretty cool. There's really not time to cover it particularly well. The alphas are like the joint probability of the current state and the past observations. So that's sort of like something that contains all the information about the past. Alpha is the past information. The betas are the conditional probability of the future observations given the current state. So the betas are the future. The betas are the future, the alphas are the past, okay? So the interesting thing is that you can express the distribution. So if you multiply the alpha and the beta together, you get something which is easily shown to be the joint distribution of the current state and all the observations. Is that kind of clear, maybe? You've been hanging around this class long enough that this is all the future Y's. This is the present and the past Y's, okay? The alpha includes the present. So if you take the union of the present, the past, and the future, you get everything. So this is the joint distribution of everything, but it also includes the distribution of at the state of time y, okay? So if you know that, if you know this, you know the distribution of x, and because now what you could do is just normalize this by over j, by summing over j, and you have the posterior distribution of x given all the y's. My point is, if you know this thing, y's are the data, that's constant. If you know this thing, then you know the distribution of the state x. What I don't know is how do I compute the alphas and the betas? So my point is, if you know the alphas and the betas, you can compute what you need. Okay? I didn't tell you how to get the alphas and the betas. Oh, I can also do this, which is even more important. Well, differently important. It's not more important, it's just differently important. It's differently important because I can also get the probability distribution of pairs of states, which I'm going to need. Because if I want to compute the expectation of decay statistic, I have to have the statistics of pairs of states. Okay, does that make sense? Any questions with that? Of course, through a slightly more complex expression that also involves alpha and beta, okay? Same basic idea. But the real question is, how do I get the alphas and the betas? Okay. There's a recursion for the alphas. You can compute the alphas by recursing in time. So the alphas are computed like with a forward iteration. You know, it's like, not that I really know how to do this, but does anybody knit here? Like, are there any knitters? Knitting is kind of, I don't know if you know this, but knitting is sort of like cool again or something, at least among some people, okay? Because it's very recursive. First of all, people know what knitting is, right? Okay. Oh, there's like at CMU, in their department of machine learning or something, they have a number of knitting people. They have people who specialize in knitting. That's their research area. Okay, it's a material science problem. You see, it's very interesting, right? The interest keys are basically creating these recursive knot structures, okay? So So what happens is that when you do this sum, it's like knitting. Okay, purl 1, knit 2, something like that. You're sort of like recursively doing this thing where you keep pulling in one more measurement, okay, with each step. And you sort of thread it back into the alpha. And this recursion, you can go through it and convince yourself, okay, that it works. So you do a forward iteration to get the alphas. And not surprisingly, you do a backward iteration to get the betas, okay? So this gives you, so here's what happens. You calculate the alphas with a forward recursion. You calculate the betas with a backward recursion. Once you have the alphas and the betas, you can calculate the posterior distributions of the x's, okay? With the posterior distribution of the x's, you can compute, remember the whole thing with the EM algorithm? In order to implement the EM algorithm, all you have to do is just put little bars over the k's. Okay? How do you put the bar over the k? You just compute its posterior expectation. So you take the expected value of this, you can do it now, because you have those from the alphas, you have those from the forward-backward algorithm, produces what you need, okay? And that's what the updates are. So to do the EM algorithm for hidden Markov models, you use the forward-backward algorithm to compute the posterior distributions of the x's. You use those posterior distributions to compute the barred statistics. I didn't talk about the b's and the s's, but the b's and the s's are the same as we had before when we were doing estimation for the mixture of distributions, right? And then you update the parameters and you repeat. Right? So that's how it works. And it's pretty clever, huh? So that's how the forward-backward algorithm works for the EM algorithm. And this is where the EM algorithm got its start, really, because it got its start on training hidden Markov models. And in those days, it was called the Baum-Welch algorithm. And then they kind of renamed it in honor of the people who reinvented it. Okay, and that's pretty much it. So I went through that like at lightning speed, but on Monday I want to do stochastic sampling because that's an important topic. So I kind of blew through at least I hopefully give you the flavor. So the summary is that to train a hidden Markov model, you use the EM algorithm. The EM algorithm requires that you know the posterior distribution of the states. To get the posterior distribution of the states, you run the forward-backward algorithm. The forward-backward algorithm is this very clever algorithm that's like knitting. And it allows you to calculate recursively the posterior distribution of the states given the data. Okay? So I'll see you on Monday. Thanks for being patient. Bye.